Hey folks, welcome to this episode on equilibrium applications. What we're going to be looking in this episode is a few different situations where equilibrium is applied to daily occurrences. We're going to be looking at diving, we're going to be looking at carbon monoxide poisoning, and also something called the Haber-Bosch process. So the first thing we're going to look at is diving. If you ever have dived before, or you were to get it certified, you'd have to actually go through a session that looks at gas laws. The one that looks at is Boyle's law, the one relating pressure and volume. Now, the reason that this is important is that as you go deeper, the pressure on your body increases, and that's because of the weight of the water. So in a normal circumstance, even when we're here in normal air and atmospheric pressure, we're inhaling a lot of nitrogen and oxygen at the same time. And in diving tanks, you also have a combination of nitrogen and oxygen. As you descend farther and farther and farther into the water, the pressure around you is again increasing. For every 10 meters that you go down, you have about one more atmosphere of pressure on your body. Now, if you remember back in previous studies of gases, as you increase the pressure, the solubility of these gases increase. So as you are breathing this nitrogen and oxygen from the tank, and the solubility of these gases is increasing, the nitrogen and oxygen is dissolving more into your bloodstream. So as you go down, you're going to have more and more and more gas dissolved in your bloodstream. Now this is a problem in itself, because if you have too much nitrogen in your blood, this can cause more confusion, drowsiness, impairment, and even unconsciousness. And this is nothing you want when you're actually down in the water. One of the other problems is that if you descend too fast, these gases can escape because you're having a decrease in pressure. The solubility of these gases decreases and they escape out of your blood. The problem is that if they do so, they create little bubbles, and these things can get lodged in a whole bunch of different places in your body. It can get lodged in joints, it can get lodged in different tissues and even organs, causing embolisms. So when you look at divers, they usually ascend very, very slowly. And if you've ever seen any movies, sometimes they ascend too fast because maybe their oxygen line is cut or whatnot, but they end up going into something called a compression chamber or bariatric chamber. And this is to re-dissolve the bubbles into the blood and then slowly bring them out of that increased pressure. Now, if these bubbles get trapped in between joints, like we see over here, you start getting something called the bends, and it's a very, very painful condition like I said, is very, very extremely painful, and that's because the bubble has dissolved out or has been gone out of the blood and has lodged itself in some kind of joint. You can also get different skin conditions like this that are typical of some of the more extreme cases of the bends. If you descend way too fast, then again, all these bubbles that are coming out of your blood are trying to be exhaled, and if you're not exhaling fast enough, you're going to have a buildup of gas in your lungs, which could cause your lungs to rupture. And obviously, I don't have to tell you, that's not a good situation. Another point where we see equilibrium is in carbon monoxide poisoning. Hemoglobin, which is this protein over here, it has 4 binding sites for oxygen, and we rely on it to transport oxygen all around our body. Again, we get oxygen through our lungs, and here we have our gas exchange between our lungs and our little capillaries, and we can see over here. So oxygen gets into our blood, and it's transported through our tissues, into our tissues and our organs through hemoglobin. However, carbon monoxide, which is created from incomplete combustion, for example, it can bind to hemoglobin much more readily. Okay, so its Kc is about 250 times greater than the Kc of oxygen. And if we remember what a Kc is, it means that it's going to favor the products over the reactants. So it's going to effectively displace. If we had both oxygen and carbon monoxide, it will effectively displace oxygen and bind more readily onto the hemoglobin, and that will be transported to your tissues and your organs. Now again, because we have a high Kc, it means that once it's binded onto this oxygen, it's not going to be displaced. It's going to stay on there, and effectively that red blood cell is no good anymore. Oxygen, when it goes into your tissues, it actually has a lower Kc, and therefore it displaces off and it goes into your tissues. But once this bonds on, you're pretty much done. And if a lot of your blood cells are bonded to the CO, you're effectively asphyxiating the internal sides of your body. So instead of having someone choke your neck or something like that, and you're not getting enough oxygen, you're simply you're still breathing in oxygen, except what you're transporting around your body to your brain, to your internal organs, to your tissues, everything that requires oxygen is not getting it. And so if effectively what happens is that it asphyxiates, and you get tissue death. And if it goes so bad as to getting organ death, that can create death in itself. One of the telltale signs of carbon monoxide poisoning is this kind of pinkish hue for people that have lighter skin, and it has to deal with, again, some of the effects that it has on some of the vessels. Another place where we see equilibrium is ocean acidification. As we burn more and more fossil fuels, now we're trying to get away from this, but in my generation, there was a lot of fossil fuels being burnt everywhere. We have coal factories that were near residential areas. We spent a lot of expelled a lot of CO and a lot of CO2 from our cars that didn't have catalytic converters. There's a lot of CO2 that was entering into our atmosphere. We're making steps to reduce that, but still there's a lot going in. Now, as we increase this concentration of CO2 in our atmosphere, we're also increasing the amount that actually dissolves in our water. So we see we have a few equilibrium reactions over here. Now, as we increase more CO2 in our atmosphere, that will dissolve into water to create carbonic acid, and that's an acid that's going to be found in our water. Now, this carbonic acid, as we see this, so again, LCP, Le Chatelier's principle, as we increase this, we'll see an equilibrium shift to the right to produce more of that. Now, if we produce more of that, over here, for example, that will mix with more water. And again, LCP will tell us that if we have more of this, we're going to see an equilibrium shift to the right. So we create this hydronium ion, which is just H plus reacted with the water. And in this case, what this is going to do is it's going to lower our pH, okay, of our water. It's becoming more acidic. At the same time, as we produce more of this, we're going to stimulate this reaction over here. So again, Le Chatelier's principle, if I create more of this hydronium, I'm going to stimulate this reaction over here. And LCP predicts that this equilibrium will shift to the left to use up CO3 2- to produce water and more bicarbonate ion. Now, the question is, where does this CO3 2- come from? Again, this is bicarbonate ion. It comes from all our coral and our shells of our shellfish. So again, here's our little process. As we're increasing carbon monoxide or carbon dioxide, we're dissolving with water, producing our carbonic acid. This breaks down into hydronium, or just H plus in this case, and our bicarbonate ion. And then that hydronium ion reacts with shellfish, for example, takes their CO3 and produces more bicarbonate ion as well. So once again, this bicarbonate ion comes from the calcium carbonate that makes up the shells of some of our bottom feeders, and also of the structure of our coral. Now, our shellfish and our coral play incredibly important parts in the ecosystem of our ocean. These act as protections for shellfish, and the coral acts as a source of food and a source of hiding for shelter for a lot of our animals in our oceans. If we break them down, then our ecosystem really starts declining. So again, we saw this process over here. As we created more hydronium ion, we stimulated the reaction in the reverse by using up more CO3, and this CO3 comes from the calcium carbonate from the shells or in the coral of our sea creatures. And so again, if we require more of this, if this is being withdrawn over here to fuel this reaction over here, which is going to the side over that way, the only way that we can create more of the CO3 is by breaking down the shells. This LCP would, if we're moving this, it would predict that equilibrium would shift to the right. And so we produce more CO3 by breaking up our shells and our coral, and then obviously killing those creatures there. Another system is blood pH. We can have systems conditions called alkalosis or acidosis. As we breathe in, we're breathing carbon dioxide. That reacts with the water in our bodies to create carbonic acid, and this carbonic acid breaks down again into hydronium, in this case our H+, just a hydrogen proton, and bicarbonate. Now, if we hyperventilate, that means that we're actually removing a lot of CO, or CO2. If we remove a lot of CO2, well, Le Chatelier's principle suggests that the equilibrium will shift in a way to produce more CO. So that means that carbonic acid is going to break down into H2O and CO2, and that also means that if I need to break this down, I first need to create it. And the only way I can create it is by joining carbonate ion and our hydrogen proton to create this acid. And effectively what I'm doing is I'm removing some of this H plus to produce this carbonic acid. Once I remove this, my pH is going to rise, aka become more basic. It becomes more basic, and that's another name for alkaline. And so eventually, if this happens, it can lead to overexcitability or even death. If we breathe too slowly, then that means that we're not exhaling enough of this CO2. If we have a lot of the CO2, it's going to push equilibrium to the left to create more carbonic acid, and more carbonic acid will create more bicarbonate and hydronium ion. Because we're producing more hydronium ion, we're going to decrease our pH, aka become more acidic, and this could cause central nervous system depression or, again, even death. The Haber process, or Haber-Bosch process, is an important process in fixing nitrogen into ammonia. It's a very fast way of doing this, and ammonia was very important in World War II for creation of munitions and bombs, but it's also very important in ammonia-based fertilizers. Now, when we look at this reaction here, we have our nitrogen reacting with our hydrogen to create ammonia, and this is an exothermic reaction because it's negative, our enthalpy change is negative. And at 25 degrees Celsius, our KEQ is 4.1 times 10 to the 8. Now, that's a pretty big KEQ. This means that it pretty much almost goes to completion. The kicker is that this is at 25 degrees Celsius. So even though we might get a lot of products, the rate of producing these products is very slow. At 25 degrees Celsius, the rates are so slow that they almost don't even happen. So what we have to do is we need to produce lots of ammonia. We need to have a way to push this reaction to really push it to the right so I can produce this ammonia and then sell it. This is our Haber process. We get nitrogen from our air, and we also get hydrogen from natural gas. And we mix these two together, and we put them in a reaction chamber. Now, this is the kind of whole system kind of laid out here. We get our different processes. We have we put them in a catalyst. We heat them. We increase their pressure, and we get ammonia. Now, the three factors that are affecting how much ammonia we can produce are these ones here: temperature, pressure, and catalyst. So we're going to go through all of these right now. When we look at temperature, and if we look at Le Chatelier's principle, and we go back to this reaction over here, again, this is an exothermic reaction. If we increase our temperature, that means that the reaction will be shifting to the left, and that's not what we want to do. So what we want to try to do is we want to try to decrease the temperatures as much as possible so that we can push this reaction to go forward. However, if we decrease our temperature by a lot, our rates effectively slow down to almost nothing. So we do need a quote-unquote lower temperature, but we can't have a high temperature because that would stimulate the reaction in the reverse direction. Now, this table shows the effect on changing the temperature on the KEQ. So you can see that at a low temperature here, our KEQ is times 10 to the 8, which means that products over reactants, products are really favored here. As we increase our temperature, you can see that our KEQ can become smaller and smaller, meaning that more reactants are favored. Okay, the reason for that is because the equilibrium is shifting to the left. So what engineers and chemists have come up with is that they need to lower the temperature to about 700 degrees Kelvin. Now, that's not a low temperature, and that's around this area over here. And you can see that the KEQ is pretty small, but at the same time, what's happening is that as we increase the temperature, we're increasing the rate. So we're not creating a huge amount of ammonia through the use of temperature, but we're creating that ammonia a lot faster. Faster means more ammonia at a faster pace, meaning more money. So again, that compromise is about getting to a temperature about 700 degrees Kelvin. Now, how about pressure? What does this do? So pressure, if we look at this, this is a nice system here, because on this side over here we have 1 plus 3, we have 4 moles on this side over here, and on this side we have 2 moles. So if we increase our pressure, Le Chatelier's principle suggests that we'll have equilibrium shift to the right. And so that's basically what happens. And again, chemists and engineers have set on a number of 200 atmospheres. You can see in this graph over here is pressure and the percent NH3 at equilibrium, and also our temperatures. And you can see that between 200 and 400 atmospheres, we have this little block over here. And as we increase temperature, our percentage of ammonia at equilibrium decreases. Now, pressure only has a slight change from 200 to 400 and 400 to 600. The change is not all that big. So we'll talk about the economical conditions in a second, but if we look at the relationship between pressure and temperature, at a temperature of about 400 degrees and a pressure of 200 atmospheres, you get almost the same ammonia as if you were to increase the pressure to 400. It's not that much of a difference. But if you had a lower temp or a higher temperature, again, because this is an exothermic reaction, we have the reverse reaction occurring, and you produce a lot less ammonia. So they settled on about 400 to 500 degrees Celsius, which is around 700 degrees Kelvin, and a pressure of 200. Now, why not? Why not just go to 400? Well, what happens is that as you go to this, your infrastructure has to get a lot bigger. Remember that you're going to 200 atmospheres of pressure. Regular conditions is 1 atmosphere. You're 400 times the pressure of normal atmospheric conditions. So that means that your pipes, your tanks, everything is going to have to be massive to be able to handle that pressure. Not only that, you're going to have more pumps, and the maintenance itself, maintaining all of these different things in working order to create that pressure, is going to be massive. So the price outweighs the benefit of going to this really, really high pressure. So again, chemists and engineers have chosen 200 atmospheres and about 700 degrees Kelvin to produce that ammonia and push this reaction this way. So again, the temperature is going to increase our rate. It's not really going to increase our push to this side, but it will increase our rate. The pressure, however, will push equilibrium to the right to create more ammonia. So collectively, we're creating a faster rate and we're creating more ammonia. Now, catalysts are the last little piece of the puzzle. These rates, even though we're increasing the temperature, they're not going fast enough. We really need to create this ammonia. So we've used a catalyst that's based on iron, aluminum oxide, and potassium oxide as a catalyst for this reaction to occur. Now remember, a catalyst speeds up the rate of reaction in both the forward and reverse direction. But because we're pushing this reaction to the right with pressure and also increasing the rate with temperature, we're going to be creating a lot of ammonia in a short amount of time. So that's it for now. Thanks very much for watching. We'll see you next time.